So 14c energy calculations is basically an extension of what we did in 14b. So we looked at the definitions of specific heat capacity and specific latent heat. So all we need to do now really is assign an equation for those two definitions and see how we can use those in calculations in exam questions, for example. So literally looking straight at the two equations for these two different definitions, you've got specific heat capacity C, and the equation, the definition is there again. And the equation which is given, so both of these equations will be given in the exam at the back of the exam paper. The equation for specific heat capacity is Q equals mc delta theta. Now that's in symbols, but it also gives you the equation in words as well, so you can check that at the back. So Q is the change in thermal energy, so that's either if you're heating up a substance, so you're adding thermal energy to that system, or the release of thermal energy, for example, if it's cooling down. So Q, the change in thermal energy, M, the mass of the substance, so the mass of the substance that you have that you're heating or cooling, the specific heat capacity C, and then delta theta, which is just a change in temperature. So because we know that specific heat capacity is defined as how much energy is required to change the temperature of 1 kilogram by 1 degree Celsius, if we use this equation, we can actually find out, well, how much thermal energy might be transferred if I have a specific mass M. I know the specific heat capacity C of this substance, and I have a specific change in temperature which might be 20 degrees Celsius or even more. Okay, so C was defined as the property of the material, and now we can use this equation Q equals mc delta theta to actually use in calculations and determine different amounts of change in thermal energy. Specific latent heat, which we said, again, the definition was how much energy is required to change the state of 1 kilogram. So that's L, the latent heat of the substance, so it's a property of a specific substance. And the equation that we can use for this is Q equals ml. So very similar to mc delta theta, but in this case there's no delta theta because it's a state change, so there's no change in temperature. So Q again is the change in thermal energy, M is the mass of the substance that we're specifically trying to change the state of, and L is the latent heat of that substance for that state change. So they're the two equations. They're both given in the exam. All you need to be able to do is rearrange them and use them. So if we just rearrange them first of all, if we have Q equals mc delta theta and I was asked for the mass, so if I'm changing temperature, how do I know which one I have to use? The easiest way to actually determine that in an exam is to ask yourself, well, am I working with a temperature change? If I am, and the temperature of a substance is changing, then it will be Q equals mc delta theta, the specific heat capacity. But if I'm dealing with a state change, whether it's evaporating, melting, condensing, then it will be Q equals ml for the latent heat. So temperature changes are mc delta theta and state changes are Q equals ml. And some questions, which we'll have a look at in a second, can actually require the use of both in one question. So you may be changing temperature at some point, and then you may get to a state change where you have to use both equations in the question. So rearranging them, if I were asked for M, in the change in temperature question, so it's Q equals mc delta theta, M is equal to Q, just divide the C delta theta. So Q divided by C delta theta equals M. Same if I was looking for C, divide by M delta theta, so Q divided by M delta theta. And finally, if I was asked for delta theta or asked for the change in temperature, then it's Q divided by MC. So essentially, whichever element of this equation you need, if it's one of the MC or delta thetas, then you just divide by the other two. So Q divided by the other two elements that you don't need. And then this one, same again, it's very simple. Q equals ml. If they ask me for M, I divide by the L, so Q divided by L. And if they ask me for L, I divide by the M, so Q divided by M. So again, it's really straightforward. It's just divide by what you don't want, or the one that you're trying to get rid of on the same side of the equation. All right, so it's just a division to rearrange. If we actually have a look at a specific question, for example, you're heating 0.65 kilograms of gold, so the units of that mass are absolutely fine. I don't need to convert the units. 0.65 kilograms is as it should be. In attempt to melt it from a starting temperature of 25 degrees Celsius, so at least I know the starting temperature. It says you supply 100 kilojoules, or kJ, which is kilojoules. Now immediately what I might do in my exam is write down that that must be converted from 100 kilojoules to 100,000 joules, or use the prefix for kilo, which is times 10 to the power 3. So energy is 100 times 10 to the power 3 joules, or 100,000 joules, to the gold that you have. what mass of gold melts? Now, you have a little table here of different properties. So you've got the melting point, which is 1064 degrees Celsius. You've got the specific heat capacity of solid gold, and you have the specific latent heat of melting. Now, just check the units on these as well, because it does do that in the exam where it tricks you and it gives you the constants with a different prefix on the unit as well. Sometimes they give kilojoule and kilojoule per kilogram, so just be careful. Let's just have a look again then at the question. So we've established we've got the different values and all the units except for this one were fine, which we changed. Now let's have a look at the question again. So you're heating gold, 0.65 kilograms is the mass, in an attempt to melt it, but you're starting at 25 degrees Celsius. Now if I want to melt it, I have to be at melting point. But it says here that melting point is 1064 degrees Celsius, but I started at 25. So what I need to do initially is find the change in temperature in order to raise the temperature of the gold from 25 to the melting point. That change in temperature is 1064, subtract the 25. Okay, so we've got 1064, subtract the 25, which is 1044, 1039. So in order to get the gold from 25 to the melting point, I have to raise its temperature by 1039 degrees Celsius. So there's my delta theta in Q equals mc delta theta. I already have m, 0.65, so I've got m, I've got delta theta, and I also have specific heat capacity of solid gold, C. So I've got m, c, and delta theta. I can calculate Q from the equation Q equals mc delta theta. I can find Q, which is the energy which will be required to raise the temperature of this amount of gold from 25 to 1064. And when I do that calculation, I'll find out how much energy it took me to actually get to melting point. Now, if you do the calculation, you'll find the value is around 87,000 joules. So if it takes 87,000 joules just to raise the temperature of gold to the melting point, but I only have 100 kilojoules or 100,000 joules that I can transfer in total, then I've just spent, essentially, I've just used up 87,000 of my 100,000. So 87,000 was what it took me just to get it to melting point, to change the temperature. Now I've got 13,000 joules remaining, so 100,000 subtract the energy to get it to melting point, 87,000. 13,000 joules is all the energy I have just to melt it. I'm now at melting point. I'm at 1064. Any energy now that I input into my gold will not go into changing the temperature, but it's at melting point, so it will go into breaking those bonds down in solid gold to create liquid gold. So what mass of my 0.65 kilograms solid gold, what mass will actually melt if I have 13,000 joules? So I have Q from the equation Q equals ml. I have Q, which is 13,000 joules. I have L, the specific latent heat of melting gold, 67,000. And I'm looking for M, so M is equal to Q divided by L, 13,000 divided by 67,000, and it works out at around 0.19 kilograms. So actually, if I start with 0.65 kilograms of gold, but I'm at 25 degrees C, and I input 100,000 joules to that solid gold, only 0.19 kilograms will actually melt, because 87,000 joules was spent raising the temperature, Q equals mc delta theta, and only 13,000 joules was used to change the state, Q equals ml. So there's an example of how you might use both change in temperature and the change of state at the same time. So just be careful in terms of what are you calculating at which stage. There are other exam questions as well that can come up on 14C. There is a core practical which you needed to do for the Edexcel GCSE physics, which was one, to melt ice. So you're trying to produce that temperature time graph, which we saw in 14B, where the temperature changes of ice to raise it to 0. Where it melts, it goes flat. So there's no temperature change at a state change. And then when it's become liquid water, you can raise the temperature again up to 100 degrees Celsius, where it reaches boiling point, and then it goes flat horizontal again, no temperature change, whilst the water is boiling or evaporating to become steam. So that melting ice practical is very straightforward. You're just essentially recreating that temperature time graph. On the other hand, you might want to do the core practical where you have to determine the specific heat capacity of water. Here's an image of the setup. Basically, you have a polystyrene cup. We'll talk about why polystyrene in a second. Glass beaker, quite a large thermometer, so you've got the tripod there just to hold your thermometer in place. Now, if you're trying to determine C, the specific heat capacity of water, you need Q, the change in energy, M, the mass of the substance, and you need delta theta, the change in temperature. Now, mass of the substance is simple. You put it on a weighing scale, you zero the scale with the cup on, pour the water into the cup, and you measure the mass of the water that you're using. Change in temperature will be nice and easy because you've got a thermometer, so you'll measure the change in temperature using your thermometer. Q, the energy, the thermal energy transferred to the water, that one's slightly more difficult. But what we're going to do is we're going to use an immersion heater, which is like a metal cylinder type device. You'll place that in the water, and what happens is you'll transfer energy via the electricity. It's an electrical device, and once you plug it in, it will just generate thermal energy from the electric heating effect, which we saw in chapter 10. Now, the immersion heater is giving out thermal energy into the water, which is essentially transferring thermal energy Q to the water, which raises the temperature. Now, what we need to measure how much energy is actually transferred to that water by the immersion heater is a joule meter. Okay, so we'll use a joule meter, and it will tell us over a specific period of time how much energy have I just transferred to my immersion heater. We'll check the temperature change in that time. So the longer we leave it adding thermal energy to the water, the larger the temperature change will be. So the bigger the better, essentially. So we'll find out the change in temperature for that amount of energy. We've got the mass, and we can do C is equal to Q divided by M delta theta. So energy from the joule meter divided by mass of the water from the scale times by, on the denominator, change in temperature, which came from the thermometer. So it's very straightforward if you have a joule meter. Now, one thing to note is that the value you get is probably going to be higher than the true value of specific heat capacity for water. And the reason is the Q value, the change in thermal energy, which the joule meter told us on the device from the immersion heater. So the immersion heater is transferring thermal energy to the water. My joule meter says, for example, 10,000 joules of energy went into the immersion heater. Okay, now that's the only value of energy you use, 10,000 joules in my equation, Q on the numerator on the top, so Q divided by M delta theta, Q is 10,000. However, did 10,000 joules of energy actually go into raising the temperature of my water? Was all that energy used to heat the water? Most likely not. Even though we use polystyrene, which is a very good thermal insulator, there's no lid on here. So a lot of thermal energy that is coming from my immersion heater, that 10,000 joules from the immersion heater, some of it is going to be used and dissipated into the surroundings. So actually the true value of Q, which just raises the temperature of my water, will be less than the 10,000. So the value of Q that you use is an overestimate because some of the energy will be wasted to the surroundings. It won't all be used to heat the water. So if Q is an overestimate in the equation where Q is proportional to C, if Q is an overestimate, then C will be an overestimate, all right? And it's because of that wasted energy. Now, in order to make that more accurate and reduce the wasted energy, we just insulate it better or use more insulation or simply just place a lid over the top, which is an insulator as well. And that's the core practical for specific heat capacity.